Okay, section 3.3 talks about zeros of polynomial functions. So we're going to continue our discussion of finding factors, but we'll take those a step further and take our factors and then look for actual zeros. All right, so the factor theorem. All right, well, let's start with this up here. So we have a function. If this one's a quadratic function. And then we can write this function in factored form. So if I take that and I have two factors, I have two binomials that I could factor the quadratic function into. So x minus 1 and x plus 2. So that means that if I put an f of 1 in, right, to the original function, because that tells me that one of my zeros is 1. So f of 1 would equal 0. Right? Because again, if we think about setting this thing equal to 0, we're looking for where this function would cross the x-axis or where the y, because that's really what f of x is y, where the y would be 0. And so that's what we're asked to look for when we are looking for 0. So f of 1 will equal 0, but also f of negative 2 will equal 0. All right, this means that 1 and negative 2 are zeros of the function f of x. All right, and so that's what this theorem, the factor theorem, is really trying to say. So if we take some polynomial, so up above our polynomial was this quadratic, if we take that and we divide it, and if it's particular a binomial, like x minus 1 is a factor, then that means that f of 1 is equal to 0, or sort of said another way, when we divide this polynomial by this binomial, the remainder will be 0. Okay? And that tells us that that number, 1, is a 0 of the function. All right? So whatever that is, it's going to be the opposite of what we have in the binomial. Like in our case, it was x minus 1 or x plus 2, in which case k would be negative 2. All right, so this will, I think, make more sense when we do a couple of examples. All right, determine if the binomial x plus 4 is a factor of this polynomial. So how would we know if that is a factor? Well, we would divide and hope that the remainder would be 0. Let's use synthetic division. What goes in the box out in front when we do synthetic division? Dividing by x plus 4. So it's going to be the opposite of that, minus 4. Okay, and also check for missing term zeros. We have a degree 4, which means we should have 5 terms. 1, 2, 3, 4. We only have 4 terms, so be careful. We have a missing term. Make sure you put that 0 in. We have 3. The cubic term is missing, so that goes next. 0. Negative 48. 8. And 32. All right, leave a space for numbers. Draw in your horizontal line. Draw in your remainder line. All right, first we're going to bring down the 3. We'll multiply. That's negative 12. We add. That's negative 12. We multiply. That's positive 48. We add. That's 0. We multiply. That's still 0. We add. That's 8. We multiply. Negative 32. And we add, and the remainder is 0. So that means that x plus 4 is a factor of that polynomial, because when we divided it, we got 0. All right, so that's kind of what this is saying up here. We have a function. We divide by a particular factor. It is a factor of the polynomial because our remainder is 0. Right, so the factor theorem is kind of falls from the remainder theorem that we had the other day. All right, let's try the next one. Go ahead and pause the video and see if x plus 4 is a factor of this one. All right, so we're going to put a -4 again out in front. Degree 5, kinked, so that means we should have 6 terms. 1, 2, 3, 4, 5, 6. Looks like we have them all, so we don't have to worry about any missing terms. 1, 6, 11, 12, 5, and -20. All right, leave a space for numbers, put in your remainder. All right, so bring down the 1. We multiply, that's -4. Add, that's 2. Multiply, that's -8. Add, that's 3. We multiply, that's -12. We add, that's 0. We multiply, of course, that's 0. We add, that's 5. We multiply, that's -20. So our remainder is -40. So that means no, it is not a function. So I guess the answer here was yes, it is a factor. And now we're going to say no, it is not a factor. Okay. All right, now they're asking us to factor this cubic. Now, the only times we can really factor a cubic is if it's a sum of cubes or difference of cubes, or maybe if we could do this by factoring, right? But I think you can see pretty quickly there's nothing I can take out of the 6 and the 37. I could take an x squared out of these two, but you can see that's not going to give me 2 terms that are the same. So we're not going to do this by grouping, but the whole idea is we could try to factor this. If we knew what one of the factors were, then we could divide this. Well, we're told that 5 is a 0. So that means if we divide by the binomial x minus 5, if what they say is true, we should get a remainder of 0. And if we don't, we did something wrong, or what they said is not true. Okay, so let's do that. Let's divide through and verify that we get a 0. Now we know we're going to get a 0, but the important thing here is not that we get a 0, but what we need out of this thing is the depressed polynomial. Because together with this binomial, the depressed polynomial, essentially our answer of the division, will be the factorization of this cubic that we don't have any other way to do. Okay, so we'll talk more about that when we're finished. All right, so what goes in the box? Remember, it's the 0 that goes in the box. So 5, the opposite of the binomial. All right, degree 3, we should have 4 terms. 1, 2, 3, 4, all looks good. So we're going to put a 6, -37, a 32, and a 15. All right, draw in your line, draw in your remainder. All right, bring down the 6. We multiply, that's 30. We add, that's -7. We'll multiply, we get -35. We add, that's -3. We multiply, we get -15. And the remainder is 0. Now, we knew that remainder was going to be 0 because they told us the 5 is a 0. They didn't say check to see if it is. They told us it was. So there was really no doubt that we should get this. However, this is really what we wanted, the depressed polynomial. So let's kind of rewrite what the original function was. The original function was 6x cubed minus 37x squared plus 32x plus 15. And now we have just factored that. X minus 5 times the depressed polynomial. So that's going to be 6x squared minus 7x minus 3. Remember that this first term to the right here is the constant, right? Is the constant. Then the next one is the linear terms coefficient. And the next one is the quadratic term coefficient. So also remember that we started with degree 3. We're dividing by a degree 1. this will be a degree 2 coefficient, degree 1 and constant. So the degree of our answer is always 1 less than the degree we started with because we are dividing by a binomial, linear binomial of degree 1. Okay, so we may or may not be finished. What we want to think about is, okay, we don't need to do synthetic division anymore because we took this cubic, we factored it into a binomial and a quadratic, and then we know how to factor quadratics. When they're factorable, we know how to factor these always. So let's assume for right now that it is factorable, and let's rewrite it. So we want to now factor that quadratic. We're just using the factoring methods, that we learned in Algebra 1. So let's see. I'm going to assume it's going to be 3x and 2x. The signs are different, so we'll leave them off for now. 3 and 1, I know I can't put a 3 here, so it's going to have to, if it's factorable at all, it's going to have to be a 1 and a 3 there. And let's see, we get 9x, we get 2x, that difference is 7x, that's good. So we need the 3 to be negative, so we get a negative 9x and a positive 2x. All right, and so that's it. We have now shown how we could take a cubic that we can't otherwise factor, and we've been able to factor it. Now, they kind of gave us a little help by telling us that 5 was a 0. Essentially, it told us what one of the factors were. In the next lesson, next unit, we're going to have to kind of do that on our own. But for now, they're going to sort of give us a little help a little bit. Or actually, I think right in this unit, in the next thing we're going to do is we're going to figure out how to get this starting point on our own. We're going to try a couple of things and see which one gives us that remainder of 0, and as a result, then we can start factoring. Okay, so let's read through this paragraph here. In the previous example, 3 linear factors, x minus 5, 2x minus 3, and 3x plus 1, have constants whose product is the same as the binomial constants. So in other words, have constants. So the constants that we had were negative 5, negative 3, and 1. When we go to FOIL this thing out, right, if we were to FOIL, expand this, multiply all this together, we would get this original polynomial, right, a cubic. But at some point, this negative 5, this 1, and this negative 3 would get multiplied together and give us 15. Not a coincidence that 15 is the constant in the original problem. All right. Also, the leading coefficients of the 3 terms. So this was a coefficient of 1, this was a coefficient of 3, this is a coefficient of 2 in the 3 factors that we have. So the 3 factors have a product equal to the leading coefficient of the original polynomial. So 6, again, that's not a coincidence that 6 is up there. All right. Furthermore, the 3 resulting zeros. Now, we would usually just say 5 because they gave us the 0 is 5, but I'm writing it as a fraction. So 5 over 1, that's one of our zeros. 3 over 2 and 1 over 3 have numerators, which are all factors of the polynomial's constant. So the numerators of these fractions, 5, 3, and 1, are factors of the constant, 15, and the denominators are all factors of the leading coefficient of the original 6. So that is a way for us to sort of guess at what numbers we should try, all right? So like I know I wouldn't try the number 10 as a possible 0 because 10 is not a factor of 15, right? Does that make sense? So we're going to use this rational zero theorem to come up with possible zeros that we might want to check. So that, right now, this last example, they gave us one of the zeros. In the future, they're not going to give us that. And we're going to have to come up with possible zeros ourselves. And that's what this theorem is helping us. So the rational zeros theorem. So if I have a particular fraction and it's reduced, and it is a 0 of our polynomial, then the polynomial function with integer coefficients. So that means, we have to have integers, like square roots and things in there. So, so if P over Q is a reduced rational number, so it's a fraction reduced, and it's a zero of the function, then the polynomial of f of x, the polynomial function, then P, that's the coefficient, that's the numerator, P is a factor of the constant term, and then Q, the denominator, is a factor of the leading coefficient. All right, so let's list what we're talking about. It'll make more sense when we actually do an example. So consider this following polynomial. All right. What we want to do is we want to list all of the possible zeros. So using our theorem up above, right? We know our leading coefficient is 8, and we know our constant at the end is 4. So we want to list all the possible zeros for this particular quartic polynomial. All right, so again, it's P over Q, so it's the values of all the factors of the constant divided by all the factors of the leading coefficient. All right, so if we want to, we could think of it as, okay, so 4, and then 2 and 1, but plus or minus all of those. So those are all the factors of the constant divided by all the possible factors of the leading coefficient, which is 8. So we have 8, 4, 2, and 1. Now I don't need plus or minus on top and bottom, but I'm going to take every number upstairs and one at a time put it over numbers that are downstairs. Does that make sense? So I'm going to do 4. I'm going to kind of do it in reverse order, I guess. So let's say 1 over 1. All right, so plus or minus 1 is a possible 0. And then 1 over 2. So plus or minus 1/2 is a possible 0. 1 over 4. So plus or minus 1/4 is a possible 0. 1 over 8 plus or minus 1/8 is a possible 0. All right, now we switch to the next one, 2. 2 over 1. All right, that's plus or minus 2 is a possible 0. 2 over 2, well, that's 1. We already did that. 2 over 4, that's 1/2. We already did that. We don't need to replace it, write it again. 2 over 8, that's 1/4. We've already got that one in, so we don't have to write that one again. All right, and now let's go to the last number on top, 4. So 4 over 1, so plus or minus 4 is a possible 0. 4 over 2, well, that's already plus or minus 2. We already did that. 4 over 4, which is 1, we already have that one. And 4 over 8 is 1/2. We already have that one. All right, so if there are any rational zeros, and there may not be any rational zeros, but if there are rational zeros, they would have to come from this list. So that means using synthetic division, we would only need to check 1, 2, 3, 4, 5, 6, 12 possible zeros, if there are any. And again, there may not be any. They may all be irrational. They might be complex. We don't really know. But if there are rational zeros, they would have to come from this list. Now you might say, well, that's 12 numbers. That's a lot. But it narrows it down from infinitely large list of possible zeros down to 12. Okay, so now our goal is to check these. Which one of these work? All right, so if you look, we have a degree 4. We really only need to find 2 of our zeros. So remember here, we started with a degree 3. We found a 0. Well, they told us one. Once we divided it by that, we got a depressed polynomial of degree 2. So if you think we're starting with degree 4, let's say we find a 0, we're going to have a depressed polynomial of degree 3. We have to find another 0, divide again, and then we'll get a depressed polynomial of degree 2, which is kind of like what we had here. And then we'll be able to factor it. or use quadratic formula to find the other zeros. Okay, so here we're not just trying to find factors, we're going a step further, we're trying to find zeros. Okay, so up the previous problem, they were asking for factors, and so we were done once we got our factors. But if we had been asked to find the zeros, we would just set each of those equal to 0. And so that's kind of what we're going to do here. All right, so let's just try. Now we're going to use a new sort of method for synthetic division, which just takes a little less space and a little less time, but it takes a little bit more concentration. So we're going to set it up a little bit differently, because we don't know if the number we put in is going to work, so we're going to just have to try potentially quite a few numbers. All right, so let's set it up like this. So the x is the 0 that we're going to try, and then let's put in the coefficients like we're doing synthetic division, but this is a shorter version yet of synthetic division. Yes, synthetic division is already a shorthand version of long division, but now we're going to do an even shorthand one. All right, so let's see. Degree 4, so that's a quartic. We should have 5 terms. 1, 2, 3, 4, 5. So we're good. We have no missing terms. We have 8, negative 26. We have negative 27. We have 11, and we have a 4. Okay. All right, so what we're going to try to do is just lightly put a line there. And, if the number we put here is a 0 of the polynomial, then that means we'll get a 0 here. If not, we'll move on. We don't really care what the remainder is. What we really care about is if the remainder is 0, then we care about this depressed polynomial that's going to be in here. If it's not 0, we don't care, we move on, because then we know the number we tried is not a factor. So let's start with, let's just try with the number 1. All right, so this is synthetic division. So it's like we're doing a 1, and then we're doing 8, negative 26, negative 27, 11, and 4, and we're doing this. Except we would have to keep rewriting this for every number we try. Here, we're just going to do one number. So what we don't do is we don't put these numbers down. We only put these numbers down in the table that we're creating now. All right, so we bring down the 8. So that means we just bring down this 8. We multiply 1 times 8, and that's 8. And then we add it to negative 26. So this takes a little bit more concentration. So we have 8, and then negative 26 plus 8, that's negative 18. So again, we're not putting the number here. We're just, in our minds, putting the number and adding it down and getting negative 18. Okay, and then we would multiply the 1 by the negative 18 and put that number up here, except we're not doing that. So we do 1 times negative 18, that's negative 18, add that to negative 27, and that's negative 45. Okay, so again, it takes a little bit more concentration. We multiply 1 times negative 48, add it to 11, that's negative 34. So at some point, I think you can see that this is not going to work, right? This number times this should be negative 4, and so it's just not going to work. So we don't care about it. We almost like want to just ignore this whole thing. We'll bring this down, and now let's try a different number. So let's try negative 1. All right, and so we're really just going to ignore those numbers that we had there, and now start the process over again. So let me just kind of like cover those up if that helps you. And so I'm going to bring down the 8 again. Negative 1 times 8. Negative 1 times 8 is negative 8. I'm going to add that to negative 26. That gives me negative 34. Now negative 1 times negative 34 is 34. Add that to negative 27, and that's a positive 7. And multiply. That's negative 7. Add that to 11, and I get a positive 4. And now this is looking good. Negative 1 times 4 is negative 4. Add that to 4. that gives me a remainder of 0. All right, so we have found one of our zeros, right? So we know that x equals -1 is a 0 of the polynomial because it had a remainder of 0. Now we have this depressed polynomial that we're interested in. So now we sort of start over. We don't go back and we use the original polynomial anymore. It's like we did before when we found this depressed polynomial, we then try to factor that. We don't go back and try to factor the original problem. So same thing here, we don't go back and try to find another 0 of this, we try to find another 0 of that. All right, now we should, so my question is, should we check 1? Should 1 be checked again? And the answer is no, because if 1 is not a factor, I mean, think of it as like a number, right? So if I said 25, oh, let's see if, let's say 125. All right, so like, oh, I'm trying to find factors of 125. Let's see if 4 is a factor. No, 4 is not a factor. Okay, I checked it, it's not a factor. Oh, 5 is, so I do that, and I take this and I say, oh, that's equal to 5 times 25. So 25 is like our depressed polynomial. I wouldn't try 4 again. If 4 wasn't a factor up here, it's not going to be a factor of a smaller number, right? The smaller factor. So same thing, this polynomial is a factor of the original polynomial. If 1 was not a factor of the original, it's also not going to be a 1. It's not going to be a factor of this one. However, -1 might be. So you should get in the habit of actually checking -1 a second time. It could be what we call a repeated root. So you should try that. So we're going to ignore all these other numbers now. If you want, we can kind of cover those up. This is the problem that we're dealing with. So we're going to bring down the 8 and multiply -8 plus -34, so that's -42. And then we multiply -1 times -42, that's 42, and we add that to 7, so that's 49. Oh, and also the remainder line is now moved back 1, right? Because now this is our polynomial, so we have our remainder line there. But you can see that's not going to work, right? I need this -1 times 49 to equal -4, so that we'd get a 0 here, but that doesn't work. And really, as soon as you know it, these numbers are not important at all if this is not going to be a 0. So as soon as you realize that that's not going to be a 0, you can simply move on. All right, so now we want to think about ignoring that, and let's try another number. So we have, remember this, let's write what we have as we go along here. Let me get rid of this so we can have space. So the original problem, let's rewrite that. So 8x to the 4th minus 26x cubed minus 27x squared plus 11x plus 4. That has been factored into x plus 1. Remember, the 0 is x equals -1, so the binomial would be x plus 1. And this depressed polynomial, so 8x cubed minus 34x squared plus 7x plus 4. So you can see that what we're doing, right? So now we got to try to factor this thing. And so now we're looking for factors of this. Now we found out that -1 is not a factor, that x plus 1 is not a factor of this because x equals -1 was not a 0. So let's try another one. Let's try 2. All right, so I'm going to bring, now again, we got to ignore that, that row didn't work, so we're going to ignore that, and we're just going to use the depressed polynomial numbers. So we bring down the 8, 2 times 8 is 16, add that to -34, and that's -18. We multiply, that's -30, that's -36. And we add that to 7, and we get -29. And you can see again that's not going to work, right? So we can move on. All right, so we can ignore both of those numbers. So let's try -2. And again, I'm pulling numbers from here Generally, I try not to use the fractions. I'll try the whole numbers first, the integers first. Then, if necessary, then I go to fractions. But ultimately, how many more do I need? I really only need to use this method to find 2 zeros, because this is degree 4, right? I find 1 0, I have a degree 3 with it. I find another one, my depressed polynomial is going to be degree 2. As a result, I'm done using this method. I can use factoring to find the other zeros, or I could use the quadratic formula, right? I don't want to continue this process once my depressed polynomial is degree 2, once it's a quadratic. All right, so let's try -2. We bring down the 8. So we kind of continue these numbers down, these rows down. So we brought down this 8. Multiply, that's negative 16. Add to that, that's what, -50. Multiply, and I can already kind of see these numbers are way too big. This is not going to work, right? That's going to be 100. Add to this. Now, that's just too big of numbers. All right. Let's try, for the sake of time, let's go ahead and try 1/2. All right. So we bring down the 8 now. Again, we're still sticking with these because I don't have a fat enough pencil to cross off all of these, but we're going to ignore all those lines and we're just going to still stay with 8. That's why I kind of start with a new line here to help me, my eye kind of goes back up to the 8 every time. So I bring down the 8. All right. 1/2 times 8, that's 4. Add it to -34, that's -30. Half of that is -15. Add it to that, that's -8. Continue that line down. Half of -8 is -4. Add it to 4. Boom, we have our other 0. Okay, so that means x equals 1/2 is a 0. So let's say we have x plus 1. And then what binomial would this 1/2, x equals 1/2 be? That would be 2x minus 1, wouldn't it? If I set that equal to 0, move the 1 over, divide by 2, I get x equals 1/2. So the other part of this is simply our depressed polynomial. And so that would be, let's see, let's do 8x squared minus 30x minus 8. Okay, and so let's go ahead, and so that's what we have here, right? I mean, I'm taking this these numbers represent depressed polynomial, but that is what we factor this cubic into. All right, so we have 8x squared minus 30x minus 8. And that is the factorization of this thing. Now, we would want to find zeros, though. So, I mean, we already found these, right? This one's going to be x equals -1. That's 1, 0. This one is going to be x equals 1/2. We already have that. Now, what we want to do is factor this thing, if we can. If not, we'd use the quadratic formula. So we set that equal to 0. So we have 8x squared minus 30x minus 8 equals 0. Let's first divide through by 2, right? That would, divide everything by 2. It's an equation. We can do that. 4x squared minus 15x minus 4 equals 0. And then let's see if this would factor. If it factors, great. Then we can really easily find our 2 zeros. Let's see. I think you can see that a 2x and a 2x will not work here, because if these are 2 x's, then when I find two things that multiply together give me 4, one of them is always going to be even. Either 2 and 2, that won't work. 4 and 1, that won't work. So I think we're going to have to, in this case, use a 4x and an x. And then I can't use 2 and 2 because then the 4 has the 2 next to it. So I'm going to have to use probably a 4 and a 1 in order to get this to work. Let's see. My outer is 16. My inner is 1. That's a difference of 15. So minus and plus. And so finally, I'm now ready to write my two other solutions. This is going to be x equals negative 1/4. And x is equal to 4. So if we had kept going, I kind of said, oh, these aren't working, let's try going to a half. I think the next thing I would have probably tried is a 4, and that would have given us that solution. So we would have had, these two binomials at the end. But it doesn't really matter which zeros you find, so long as you find 2 using synthetic division. That gives us a depressed polynomial of degree 2 that we can either solve by factoring, or if we needed to, we could use quadratic formula. Okay. So let's move on then to the next page and try a couple more